Good morning, students. Myself, Vijay Shankar from EC Department, Chipdol Engineering College. Today, we are going to start the last chapter of the EC students, that is Laplace Transform 5th unit. And for the third year triple students, is also the 5th unit, but it is not the last unit, my dear students, the Laplace Transform. We already discussed about the Fourier series, Fourier transform. And now, we have to learn the another analog waveform, analog form, the time domain to the frequency domain conversion, the Laplace transform. This is all it is a analog only. The next one is a Z transformation is there for the digital. In terms of the digital, all it is integral values. When you go for the Z transformation, that is for the discrete signals only, not for the continuous time signals. So let us see the definition of the Laplace transform. Why you are converting the time domain function to the frequency domain function using the Laplace transformation. So the first one, the Laplace transform is another mathematical tool. The Laplace transform is another mathematical tool for analysis of signals and the systems. The Laplace transform is another mathematical tool used for analysis of signals and the systems. Laplace transform provides border characterization of signals and the systems compared to the Fourier transform. Laplace transform can be used for analysis of unstable systems where Fourier transform has limitations. There are two types of Laplace transform: bilateral, nothing but the two-sided Laplace transform, and second one is a unilateral, nothing but the single-sided Laplace transform. Bilateral and unilateral. So both are the same. At one property only, there is a difference of bilateral and the unilateral. Remaining is all it is similar to that of bilateral and the unilateral. So only simple definition saying it is a unilateral is for positive real axis. Bilateral means including the negative real axis also. Minus infinite to the 0 and 0 to infinite, there is a two-sided, left-sided and the right-sided. Two-sided, it is from minus infinite to infinite means bilateral, we can call it as. Unilateral, we can take only from the 0 to infinite. Only the positive real axis. Okay. The Laplace transform is another mathematical tool used for analysis of signals and systems and provides a border characterization of signals and the systems compared to the Fourier transformation. The Laplace transform is used for analysis of unstable, and the Fourier transform has some limitations. There is two types of Laplace transformations, bilateral and unilateral. And the definition of the Laplace transformation, the bilateral Laplace transformation definition is f of s is equal to s. Still now, we learn the Fourier transformation. We learn the Fourier transformation is x of omega in the frequency, x of k, Fourier series, x of k is a Fourier series, x of omega is a Fourier transformation. Now it is a x of s, Laplace transformation, s value. Okay, x only. Here I am taking the inside, there is f of t. So what is the definition saying that x of s is equal to, since it is a bilateral, the limitations is from minus infinite to infinite, converting of a time domain function, the signal x of t, e power minus s t dt. Here inside I am taking the f of t, so the frequency is the f of s. Here the integration is taken from minus to the plus infinite, hence it is called bilateral or two-sided Laplace transform. Bilateral or two-sided because of plus infinite and the minus infinite. varies from minus infinite to 0 and 0 to infinite at the origin. So it is a single left-sided and this one is a right-sided. Both we can call it as a bilateral or two-sided Laplace transformation. Here f of t is a time domain signal, f of s is a Laplace transform. F of s or x of s. And if we take the signal x of t, the time domain signal, f of s, x of s, x of t, Fourier transformation. First we are taking the Fourier series, x of k, x of t, the time domain function, apply the Fourier transformation, x of omega. Now I am taking the x of t as a Laplace transformation, x of s. Got it, my dear students? It is a definition of the Laplace transformation. Definition of the bilateral, here the integration 2 times they get definition. And the unilateral Laplace transform is given as unilateral Laplace transform is given as, it is a repeated, my dear students, there is no anything here. Unilateral Laplace transformation is given as from 0 minus to infinite. What is a 0 minus? The new term we are hearing here, 0 minus and the 0 plus. Both are the same, equal to 0 only. 0 plus is a just above the 0. 0 minus is a just below the 0. Alright. 0 is there. 0 minus just below the 0. Before the 0 here. 0 plus is just above the 0. Both, all the 0 minus and 0 plus is both of the zeros only. Okay. F of s is equal to one-sided only. One-sided from 0 minus to the infinite. F of t e power minus st dt. Here observe that the integration is taken from 0 to infinite. The unilateral Laplace transform is mainly used for analysis of causal signals. The lower limit is taken as a 0 minus. This is to include the time just before the 0. Just before the 0. What they are saying, it is just before the 0. It can be taken as 0 plus also. It can be taken as 0 plus also. For continuous time function, f of 0 minus is equal to f of 0 plus. Both are is the same. Thus, for continuous function, the integration is effectively taken from 0 to infinite. Since the value of f of t is just before and after the 0 is the same. See what they are saying here, even it is denoted as a 0 minus. For continuous time function, the integration is effectively taken from the 0 to infinite. Since the value is f of t is just below and after the 0 is the same. The f of t and f of s is called Laplace transform pair. Laplace transform pair. Got it, my dear students? Now it can be written as f of t Laplace transform f of t, the Laplace transform f of s. The variable s is a complex frequency. F of s, f of omega, f of k, all it is a frequency only. But here the f of s is a complex frequency and it is given as s is equal to sigma plus j omega. What is the sigma here? Sigma is a real axis. J omega is a imaginary axis. Is a s plane. A plane S plane having the 4 quadrants. From 0 to the infinite is a one-sided. Minus infinite to 0 is another sided. So bilateral is totally common as a bilateral. Bilateral Laplace transform. and only if I am taking the single-sided is a unilateral signal. What is that S? S is nothing but having the sigma plus j omega is a complex frequency. The real term is a sigma and imaginary term is a omega. Alright. Now I can substitute in the definition of the Laplace transformation f of s is equal to integral minus infinite to infinite f of t e power minus sigma plus j omega into t dt. Expand this e power minus as a two terms, e power minus sigma into t, e power minus j omega t dt. Got it, my students? And the f of s is equal to integral minus infinite to infinite. Take as a single term f of t e power minus sigma into t e power minus j omega t dt. The above equation shows f of s is basically the Fourier transform, basically the Fourier transformation of f of t into e power minus sigma into t. This is a relation between of Laplace and the Fourier transform. How it is? What is the Fourier transformation formula? X of omega is equal to integral minus infinite to infinite x of t e power minus j omega t dt. Got it, my students? Now, what is the Fourier transformation? Not the Fourier, Laplace transformation definition. X of s is equal to integral minus infinite to infinite x of t e power minus st dt. So what is the s here? The j omega one. But saying that the s having s plane with a real term and the imaginary term, you can substitute here minus infinite to infinite x of t e power s is a sigma plus j omega t j omega into t dt. I substituted the s is equal to sigma plus j omega. After splitting the exponential value x of t into e power minus sigma into t as a one function e power minus j omega t dt. So now you can observe here the Laplace transformation and the Fourier transformation is both are the same. Instead of x of t, here it is x of t into e power minus sigma into t. Is a Fourier transformation function only. When it becomes a Fourier transformation, sigma is equal to 0. When sigma is equal to 0, e power 0 is a 1. And sigma is equal to 0, now it becomes of minus infinite infinite x of t e power minus j omega t dt as of the Fourier transformation definition when sigma is equal to 0 in this equation. Or otherwise you can say x of t e power minus sigma into t is a Fourier transformation only. Not only here explain that the above equation shows f of s is basically the Fourier transform of f of t e power sigma into t. So it's totally, if assuming a one signal x of t, that signal is x of t e power minus j omega t dt is nothing but x of omega. What did my students? When it is equal to the x of omega, when the sigma is equal to 0, f of s is equal to x of omega. The Fourier transformation, it becomes of Laplace transformation becomes a Fourier transformation by substituting the sigma is equal to 0. Okay, this is the relation between of Laplace and the Fourier transform. The Fourier transform is given by the above equation must exist which is actually the Laplace transform. Hence, sufficient condition for f of t to be the Laplace transform is that is definitely less than the infinite function for real and the positive values of sigma. For the real and the positive values of the sigma. Got it, my dear students? The next one is inverse Laplace transform. We know the x of omega is equal to a Fourier transformation, integral minus infinite to infinite, x of t e power minus j omega t dt as a Fourier transformation. What is the inverse Fourier transformation? Here the x of t is equal to integral minus infinite to infinite. Now the x of omega as an input and negative exponential becomes a positive exponential e power j omega t with respect to the frequency we are applying. Because it's a x of omega, signal is a frequency. Signal is a time domain, we can apply the integral with respect to the time only. Signal is a frequency, you can apply the integration with respect to the frequency. And 1 by 2 pi also. 1 by 2 pi. Now the Laplace transformation definition saying that x of s is equal to integral minus infinite to infinite x of t e power minus st dt. The definition of Laplace. And the definition of inverse Laplace transformation. What is the inverse? Here the x of t becomes now the output. X of t is equal to. And now it is a complex frequency. Complex frequency means 1 by the 2 pi j. And the integral is from sigma minus j infinite and sigma plus j infinite. Because it is a complex and the sum function, x of s and e power, here the negative exponential we are taking the positive exponential and with respect to the s frequency. Only the difference of inverse Fourier transformation as usual, the inverse Laplace transformation also. But the s is a complex frequency, 1 by 2 pi j, and the limitations also as of sigma minus j infinite to sigma plus j infinite. The definition of inverse Laplace transformation in terms of f of t and f of s, as I wrote here the x of t and x of s is a variable only. F of t is equal to 1 by 2 pi j, the integral is sigma minus j infinite and sigma plus j infinite f of s e power st into ds. Got it? Now enter the very important topic, the Laplace transformation properties. Previously, what we discussed about the properties, every time I said all the properties what we have in the Fourier series, in the Fourier transformation is also the same. 9 properties. The name is also the same. And similar transformation as a linearity, shifting property, frequency shift, convolution, and the differentiation, integration, the duality properties for the Fourier transformation, and integration properties there in the Fourier transformation only. Okay, these are some properties what we have learn in the Fourier series and the Fourier transformation. Only the definition is changed. The concept is the same. Only the definition, nothing but the mathematical expression for the Fourier series, Fourier transform, and the Laplace transformation is different, but the properties concept is the same. Have to prove the same way by using the definitions of the Laplace transformation here itself, what we did in the properties for Fourier transformation and the Fourier series also. Okay. Linearity property, time shift property, frequency shift property, differentiation property, and the convolution property, modulation property, integration property, Parseval's theorem, Got it, my student? These are the different properties we already learned in the Fourier transformation and the Fourier series. Now, the similar names what we have in the Fourier transformation and the Fourier series, here also the same. First one is a linearity property only. What is a linearity property? Saying that statement is f1 of t is a Laplace transformation of f1 of s, and f2 of t, the Laplace transformation is f2 of s. Be the Laplace, two Laplace transform pairs, then the linearity property states that the Laplace transformation of a1 f1 of t plus a2 f2 of t, a1 f1 of t plus a2 f2 of t is equal to a1 f1 of s, a2 f2 of s. Here a1 and a2 are the constants. Same equations in the Fourier transformation and the Fourier series also. The input is the same, a1 x1 of t plus a2 x2 of t. But in the frequency, Fourier series means x1 of k and x2 of k. Fourier transformation is f1 of omega and f2 of omega. Now, in the Laplace transformation, the change is a variable here itself for the within the parentheses, a1 f1 of s and a2 f2 of s. Here a1 and a2 are the constants. The proof, let the Laplace transformation of a1 f1 of t plus a2 f2 of t as an input signal. According to the definition of Laplace transformation, integral, it is not the 0 minus students, it is a minus infinite only. The properties what we taking here, all the properties for the bilateral only, not for the unilateral Laplace transformations. Bilateral. Remember that one, minus infinite to infinite, f of t into e power minus st dt. What is f of t here? a1 f1 of t plus a2 f2 of t e power minus st dt. Split the two parts. a1 integral, it is a minus infinite, my students. Minus infinite. So integral minus infinite f1 of t e power minus st dt is also the definition of the Laplace transformation. Since it is a signal is f1 of t, can write it is in frequency f1 of s. The second term also f2 of s. Got it? The linearity property. Coming to the second shifting theorem or translation in time domain. Shifting in time domain or time shift property. Simply saying shifting theorem in the Laplace transformation. Remember, and you have to, if you answer in the external examination, which property is asking, you have to see that linearity means don't write it is for Fourier series and the Fourier transformation. For which transformation they are asking the linearity? For which transformation they are asking for the time shift? That is a very important. So if you know that, but for which it is asking, they are asking for the Laplace transformation, you have to prove by using the Laplace transformation definition. The time shift property, they are asking for the Fourier transformation, means by using the definition of Fourier transformation, you have to prove the time shift property. That is a very important matter, students. Shifting theorem or the translation in time domain or time shift property. Time shift property. So what is the statement here? Let f of t is a Fourier transform, the Laplace transformation f of s be the Laplace transformation pair if f of t is delayed by the time t naught. If f of t is delayed by time t naught, then its Laplace transform is multiplied by e power minus s into t naught. e power minus s into t naught. That is, the Laplace transformation f of t minus t naught is equal to e power minus s t naught into f of s. Okay, I will explain here itself. Second property, shifting theorem. Shifting theorem for the Laplace transformation. Okay, what is the definition saying that the Laplace transformation of x of t minus t naught is equal to e power minus s into t naught x of s. Okay, now I can see the proof. According to the definition of Laplace transformation, x of s is equal to integral minus infinite to infinite x of t e power minus st dt. What is the x of t given here? The take that is x of t minus t naught. Integral minus infinite to infinite x of t minus t naught e power minus st dt. The input is shifted with the t naught samples. Let t minus t naught is equal to some p, and t is equal to p plus t naught. Okay, my dear students. And now, and the t is a variable and the p is also variable. T naught is a constant because it is a shifted samples only. The dt is equal to, apply the derivative, dt is equal to d into p. Substitute here, minus infinite to infinite x of p e power minus s into, what is the t value? P plus t naught into d suffix b, or the suffix dp, as a dt is equal to dp. Integral minus infinite to infinite x of p e power minus s into p dp and e power minus s into t naught. So this equation C is a Laplace transformation definition only. Laplace transformation definition only. X of s is equal to x of s into e power minus s into t naught. So don't think that is a x of s is equal to x of s and don't cancel this one. X of s is nothing but here you have to take the Laplace transformation of x of t minus t naught. So directly I substitute the x of t minus t naught there. Understood? So actually it is x of t only. X of t Laplace transformation is equal to, as I am substituting the x of t here. The second equation, the Laplace transformation of x of t minus t naught. Now I substitute instead of x of t here, the x of t minus t naught. Finally, we got the x of s e power minus s into t naught. Similar in the time shift property, what we learn in the Fourier transformation. What is the Fourier transformation? The x of t minus t naught Fourier transformation is e power minus j omega into t naught x of omega. Instead of j omega, here it is s only. Okay, and the omega is yes. Change of omega as the s value becomes of Laplace transformation. Okay. Now, you see here they have Laplace transformation of f minus t naught. It is don't take it is a 0 minus student. It's a bilateral only. Don't write it is a unilateral. Bilateral minus infinite to infinite. So e power minus s into t naught into f of s. Got it? Now the third property, frequency domain. Nothing but it's a frequency shift property. Complex translation or translation in frequency domain. Or it is also the frequency shift in the Laplace transformation. What is the frequency shift here? S minus A with the Laplace transformation of e power at into f of t. E power a into t f of t. Okay, instead of a as here I am taking the a value. What we got in the time domain, time shift property. Time shift property saying that t minus t naught, there is a sample is shifted in the time domain. Frequency domain is multiplied with a negative exponential with s into t naught. But now there is a change is s here. Frequency changes. Frequency is shifted with the a samples. So a, and there is no any change in the time, the t, f of t. So for the time domain signal f of t is multiplied with the positive exponential of e power at. Applying the Laplace transformation for that signal, you got the shifting occurs in the frequency. F minus SCA, f of S minus E. Okay. Now see the third property, translation in the frequency or shifting in the frequency domain. As a statement saying that the Laplace transformation of e power at x of t. I'm taking the x, they are explaining in the f terms, f signals. X of t is equal to e power a into t, not the a into t, sorry. Frequency is shifted with s minus a. Okay. I'll take the proof here. What is the definition saying? The Laplace transformation of x of t is equal to integral minus infinite to infinite x of t e power minus st dt. What instead of x of t, I'm taking that e power at x of t is equal to integral minus infinite to infinite. Substitute that is a e power at x of t. As a signal here, e power minus st dt. That is equal to integral minus infinite to infinite x of t e power. Take the common as a t value here, s minus a into t. Here I am substituting the minus into dt. So now observe here, it is also similar to that of Laplace transformation definition only. Compare these two. It is equal to x of s, but here instead of s, s minus here. So it becomes of, so I wrote here not the f, x. Okay, because I take the signal is x of t. X of s minus a. Therefore, e power at x of t, the Laplace transformation of, you get the x of s minus a. Got it, my students? There is a frequency shifted with a samples. Exponential, positive exponential is multiplied to the time domain function. But time domain is shifted with the t naught samples. Frequency domain signal is multiplied with a negative exponential with that sample t naught, e power minus s into t naught. Got it, my students? So what is here? I'm saying that is a x of t minus t naught. The Laplace transformation is e power minus s into t naught x of s. Observe here. These two are the is time shift. Is input is shifted with the t naught samples. Negative exponential is multiplied and the t is becomes of t naught. And here the frequency is shifted with the a samples. The time domain signal is multiplied with the positive exponential and s is becomes a here. S is becomes a. The t is t naught samples shifted there is t naught. And the frequency shifted with the a samples means the frequency value x s is changes as a into t x of t. Okay. Now, third example, same thing. Complex translation or the translation in frequency domain as e power at f of t, e power at f of t, e power minus st dt, f of t into e power minus, you can take as a common, s minus a into t. As the definition of Laplace transformation, it is f of s, but instead of s here, s minus a. Okay. Second property, first property is a linearity property, same as in the Fourier series and the Fourier transformation. Time shift property is also the same as Fourier transformation and the Fourier series. Third property also the frequency shift property, or it is also called as complex translation or translation in frequency domain. And shifting theorem, translation in time domain. All the three properties we have in the Fourier series and the Fourier transformation also. Coming to the fourth property, it is also in the same Fourier and the Fourier series theorem, nothing but the differentiation in time domain. Differentiation in time domain, d by dt of f of t. D by dt of f of t is s into f of s minus f of 0 minus. Here they are taking that it is a f of 0 minus. It is for the unilateral. It is for the unilateral, not for the bilateral, my students. What is a bilateral? S into f of s only. If it is any adding or the adding of minus f of 0 minus means that is for unilateral Laplace transformation. These are only properties are different for bilateral and the unilateral. Remaining all it is the same. Okay, I will explain the bilateral, my students. Bilateral, and here they are explaining that as a unilateral Laplace transformation, the differentiation in the time domain. I will explain the bilateral. And the fourth property saying that differentiation in time. Differentiation in time. Time domain. Okay. What is the statement saying that d by dt of x of t is the Laplace transformation of s into x of s. Got it? Now take the proof. According to the definition of the Laplace transformation, x of t is equal to, not x of t, x of s is equal to. X of s is equal to. Now I am taking is a x of s is equal to integral minus infinite to infinite x of t e power minus st dt. This is a Fourier transformation, not the Fourier, Laplace transformation definition. This is a Laplace transformation. Now I am applying the derivative here. It is a derivative d by dt. It is not possible by taking off the Laplace transformation directly. It is an inverse Laplace transformation. You can take x of t is equal to 1 by 2 pi j integral sigma minus j infinite sigma plus j infinite, and the x of t becomes of x of s here it is, and positive exponential with respect to the s. With respect to the s. It is a definition of inverse Laplace transformation. Now we can apply the derivative on both sides with respect to the t. So d by dt of x of t is equal to 1 by 2 pi j. There is no any t in this function. And integral is also not with respect to the time because it is with respect to the ds. So it is also constant because we are applying the derivative with respect to the time. X of s is also the constant. Only we have the t is there. So d by dt of e power st. Okay, my dear students, and ds. Now I can apply the derivative for this function only. Remaining all the terms what we have here is a constants is equal to 1 by 2 pi j integral sigma minus j omega infinite sigma plus j omega infinite plus j infinite x of s. What is the derivative of e power s into t? E power s into t. So what is the coefficient of t is a s. S ds. Now see this total function. I am taking the s towards here. X of s only, the 1 by 2 pi j, the integral minus infinite x of the. I take the s into x of s. Okay, right here, d by dt of x of t is equal to 1 by 2 pi j integral sigma minus j infinite sigma plus j infinite. Now s into x of s. You can write. I'm writing that as s into x of s as a one function. E power st ds. So according to that, it's comparing these two functions, x of t with x of s is a relation. Fourier transformation, Laplace transformation relation, x of s. Now instead of x of s, it is an s into x of s. Instead of x of t, here the d by dt. Means, therefore, d by dt into x of t is a Laplace transformation relation with s into x of s. What it matters, students? By using the inverse Laplace transformation definition, x of t is the Laplace transformation of x of s. But what we got after the applying the derivative with for the time domain function, there is a multiplication factor of s for the frequency domain function. So d by dt of x of t is a Laplace transformation paired with s into x of s. It is a bilateral, my students. I'm not taking the unilateral. For unilateral, d by dt of x of t, the Laplace transformation is s into x of s, and there is another function is there x of 0 minus also. Minus x of 0 minus. This for unilateral. And this one is a bilateral. Remaining for bilateral and the unilateral, all the properties the same, but only the difference of differentiation in time domain property. Got it? Now see the unilateral Laplace transformation property here. What is the unilateral Laplace transformation? Saying that here the function f of 0 minus is a value of f of t at t is equal to 0 minus. The t is equal to 0 minus indicates the time just before the t is equal to 0. 0 minus means just before the 0. 0 plus means just above the 0. In other words, t is equal to 0 minus is equivalent to the limit epsilon tends to 0, t is equal to minus epsilon. Got it, my students? And let us write that d by dt of f of t is a f dash of t. D by dt of f of t is a f dash of t. Consider the Laplace transformation of f dash of t by the definition. Laplace transformation of f dash of t is integral 0 minus to infinite. I'm taking the 0 minus students because it is a unilateral. 0 minus to the infinite e power minus st f dash of t. Why I am taking the f dash of t here? We are applying the Laplace transformation for the derivative f dash of t on. Now integrating RHS of the above equation by parts, we get Laplace transformation of f dash of t is equal to it is an integral of two functions. One function is a d by ds of e power minus st. Another function is a f of t. D by d, not the d by ds. Okay, d by ds only. It's not. I am saying it is the d by ds. See, the definition is integral 0 minus to infinite e power minus st f dash of t dt. Integration the RHS of the above equation by parts, we get by parts. What is the by parts here? The first signal is e power minus st and the second signal is the derivative of f of t. So e power minus st, and for the second signal, if I am applying the integration. Okay. See, the by parts I am applying, taking the first signal e power minus st. For the second signal, integral of f dash of t minus integral and the derivative of the first signal. What is the derivative here? Minus s into e power minus st, and again the integral of f dash of t dt. Okay, so e power minus st, integral of f dash of t is f of t minus integral is already we have here plus s into e power minus st. What is the integral of f dash of t? Again, it is f of t dt. Okay, so e power minus st f of t plus s into integral f of t e power minus st dt. Got it, my students? So what is the limitations now here? I'm taking the 0 minus to the infinite. Why it is a 0 minus? 0 minus is for the bilateral only. So bilateral function. So now I'm applying the infinite here. E power infinite is a 0. And here also the e power infinite is a 0 for the second function. Or otherwise, I'm taking here only the e power minus st f of t with 0 minus and infinite plus s into, and thus integral is the 0 minus to infinite f of t e power minus st dt. Okay, I'm not applying here. I'm taking only the integration. So e power minus st f of t is applying the infinite here. Infinite means a 0, the first term. Lower term, if I am applying as a t is equal to 0, t is equal to 0 means e power 0 is a 1, and f of 0, f of 0 minus, that is a lower limit. So minus, it is a 0 minus f of 0 minus plus s into, this is a definition of for a Laplace transformation only with the signal of f of t, so f of s. Finally, the Laplace transformation of the f dash of t is equal to s into f of s minus f of 0 minus. Got it, my dear students? So e power minus infinite into f of t, f of infinite minus e power 0, f of 0 minus 0 minus 1, my dear students. And s into, I take the integral value is 0 minus to the infinite. So first term is a 0 and the second term is a minus. E power 0 is a 1, f of 0 minus plus s into f of s. S into f of s minus f of 0 minus. Okay, which is proved as for the bilateral. And similarly, it is further apply the derivative square term. It becomes of s square f of s minus s into f of 0 minus f dash of 0. Still it is increases third derivative s cube means n plus 1, and it is increases, and f dash of 0 minus is a s, and finally is f dash of 0 minus. And nth term, the Laplace transformation of d power n by dt power n f of t is equal to s cube. S cube is becomes of s power n f of s minus, and it is decreases. What is the decreases here? The n minus 1, f of 0 minus, minus, and still it is a decreases, s square, and becomes of s. So s power n minus 2, f dash of 0 minus, and so on. The last value is f double dash. So last value f double dash means for square here the first double dash is there. Okay, and for 1 it is there is no any derivative, and the nth term is n minus 1, n minus 1 times double dash it is. So second derivative for the d cube by d3, and now here the derivative is f power n. Okay, double dash here, and it is a derivative of d by dt of, for nth derivative, d by dt of n power n, d power n f n minus 1, and the 0 minus. Got it, my dear students? So like that we'll get the nth derivative also. Later. Okay. Coming to the next property. So we learned the bilateral and the unilateral, my dear students, previously. For bilateral, d by dt of x of t, the Laplace transformation is s into f of s, and that is for bilateral. And unilateral for the d by dt of x of t is a bilateral Laplace transformation. Unilateral Laplace transformation is s into f of s minus f of 0 minus. Okay, unilateral Laplace transformation. Remember this one. This is only the property is a difference for bilateral and the unilateral. Remaining all the properties the same for bilateral and unilateral. Coming to the integration property. Integration property saying that so before differentiation property is s into f of s we got, but integration means differentiation is always multiplying the coefficient value and the coefficient value is writing it as in the denominator for the integration value. Okay. So the integration of 0 minus 2 to 3 f of t dt is a Fourier Laplace transformation is fs by s, f of s by the s. As the definition of the Laplace transformation, you can go as the definition of the Laplace transformation, the integration of 0 minus, actually it is a 0 minus to the t, not the infinite minus students. They're asking that integration theorem you have to prove for the limitation of 0 minus to the t only. If it is a minus infinite to t, that is a bilateral. Okay. Unilateral is also the same. Minus infinite to t, f of t dt, substitute as f of t is equal to e power minus st by minus s and integral 0 to minus infinite f of t dt. And applying the by parts, integration by parts, integration the above equation by the integration by parts, e power minus st and integral it is a f of t dt only, minus again, you can take a derivative of this function and integration of the f of t dt. Why I am not writing the first term? The first term is a 0 there. Okay, the first term is a 0. You see here, e power minus st tends to 0 as t tends to infinite. This total function is a 0. Then the 0 plus 1 by s, minus into minus is a plus, minus into minus is a plus 1 by s, integral 0 minus to infinite e power minus st f of t dt is the definition of f of s, 1 by s into f of s. What it matters to this integration in the time domain function, that is also up to the 0 to t only, matters to us. 0 to t. But as per the definition, there is a 0 minus to the infinite. Using the integration by parts, taking the definition here directly, the integration 0 to t f of t dt, and apply the integration for this one, minus, and derivative of this one is f of t, and apply again the integration here, e power minus st by minus s. The first term becomes a 0 because infinite value is there for the t function. E power infinite is a 0 and 0 total value. Got it? And for the second term only we have, that second term is 1 by s into the definition of Laplace transformation, f of s. So 1 by s into f of s. Got it, my dear students? Or you can take the integration by the Laplace transformation. What is the x of s is equal to integral minus infinite to infinite x of t e power minus st dt. Okay. Now I am taking that e power minus st, the integral is e power minus st by minus s. E power minus st by minus s. If it is a derivative, e power minus st into minus s. Okay. For this is a Laplace transformation, inverse Laplace transformation saying that is x of t is equal to integral sigma minus j infinite sigma plus j infinite 1 by 2 pi j as x of s e power s into t ds. Okay. The integration is applied for the input side. Integral 0 minus to the t x of t dt. And similarly here also you can apply the integral with respect to the t only for this e power only. In the right hand side also I am applying the integration 2 pi j integral sigma minus j infinite and sigma plus j infinite x of s, and the t term is in the e power st only. So integral e power st dt and the ds. So only the t term is variable and the remaining all it is a constants. That is also from 0 minus to the t. Got it? Is equal to 1 by 2 pi j integral sigma minus j infinite plus sigma plus j infinite x of s. What is the integral here? E power st integral is a e power st by s with the limitations of t and 0 minus into ds. Okay. So apply here the upper limit and the lower limit. 1 by 2 pi j. I'm taking the e power minus st by s with the t and the 0 minus. Upper limit I am substituting with respect to the t only we are applying. So t is substitute the t. The same will get the e power minus st by s minus e power 0. E power 0 is a 1 by s. E power 0 by s. E power 0 is a 1 minus 2. E power 0 minus we can take. So this value can eliminate the e power minus st by the s. 1 by s is there here. Again, integral sigma minus j infinite and sigma plus j infinite. After substituting the t value, there is no any change. E power minus st. And actually, if I am taking the 0 minus value, it is a bilateral, unilateral. If it is a infinite minus, infinite is a 0, the 0 by s. So x of s by the s e power st ds. Now see, now I can compare these two equations. Integral minus infinite to t x of t dt. What is the relation here? For x of t is a Laplace transformation of x of s. And integration for Laplace transformation with the of s is becomes of x of s by the s. X of s by the s. Got it, my dear students? You can do like this also. And nth term, the integration is applied for the n integrations. It becomes of s power n. See here, f of s by s power n. Understood? For the derivative, if you can apply the d by dt of nth derivative of x of t, what is the Laplace transformation? S into x of s. Now nth derivative is a n. D square means s square x of s. D cube means s cube x of s. And integration also, the second integral and the third integral you can apply. The t1, t2 and the tn. If it is a t1, s power 1. t2, s square. t3, s cube. tn, s power n. Okay. And these are the 5 Laplace transformation properties we discussed. Linearity, time shift property, linearity property, time shift property, or it is also translation in time domain. Third property, complex translation, translation in frequency domain. And fourth property, differentiation theorem, or it is a differentiation in time domain. And fifth property is the integration theorem. And differentiation property also we derive for the bilateral and the unilateral. Okay, because there is a difference for those two only. And the remaining properties we discuss in the next class. Any doubts, my dear students? Okay, thank you.